Good evening, my friends, or morning, or afternoon, or middle of the night, whenever you happen to be watching this. This is Mr. Leavenworth, one of your Calc AB teachers, coming to you with a video for 3.3, which is where we really start talking about our derivative rules. We're starting to move away from taking all those limits and finding some ways to do some things faster. Derivatives are all about how graphs change, and more importantly, it's a synonym for the slope of a graph, especially at a certain point. There's a few things that are maybe pretty intuitive or things that we should talk about real quick if you haven't spoken about them with your teacher in class. And it's those three right here. So when we take the derivative of a constant, then that means our derivative is going to be zero, because remember, the derivative of a constant function is a horizontal line. The slope of a horizontal line is zero, so therefore the derivative of any constant function is zero. That one's self-explanatory. The second and third ones are more intuitive than self-explanatory, but just like with limits, if we have a constant multiplied by a function, when we take the derivative, the derivative is just that same constant multiplied by the derivative of that function. And similarly, our third option here is if we have a sum or a difference of two functions and we want to take the derivative of that whole expression, it is just simply the sum or the difference of the derivatives. That unfortunately does not work with two functions multiplied together, or certainly a quotient of functions, or a rational function with two functions, one in the numerator and one in the denominator. That's going to come actually in our next video, 3.4, when we talk about those specific rules. Those three are self-explanatory. The rule with e to the x is just kind of fun and interesting, and the rule we are going to spend most of our time talking about today is this one right here, where we say the derivative of a power function, x to the fifth, 4x to the third, negative 9x to the 57th power. Instead of running a limit on those, we can just kind of apply this rule here, which basically says we're going to take the original exponent, multiply that by the original constant in front, if there is one, and then just subtract 1 from the exponent to get our new exponent. Each derivative should have one lower degree than the function it came from. You'll see some problems down here that are warm-up problems. Those are problems you can do on your own. They will be included in the answer key that gets uploaded eventually, but these are not problems we're going to spend time working on in this video. So take a look at those. If you want to pause me and run the problems on your own, that's totally fine. But I'm going to go ahead in just a few seconds and skip right to the actual notes, the meat of this lesson. So if you want to pause, go ahead. Otherwise, we are going to move on to studying the power rule a little bit more deeply. Okay, here we go. Power functions, I kind of described them before. They take many different shapes and forms. You might be looking at 4b and 4c and saying those aren't power functions. And I would agree and disagree with you at the same time. We'll talk about those shortly, but we're going to start with 4a. There are a number of ways to take the derivative of 4a. You could start by dividing out each term by 6, because it's a single term in the denominator. And you could do that. I'm actually not going to do that. I'm going just to treat that 6 in the denominator, since it is a constant and not a function itself, and just rewrite h of x as 1/6 times this expression in the numerator. And from there, we just have a constant times a difference of power functions, and so it is very easy for us to say that the derivative of h, remember the constant multiple just stays out front, and then we take the derivative of each term because it is a difference, and we can do that. So we're going to take the original, if we're looking at 3x to the fourth, take the original exponent times the constant, or the coefficient out in front, And so 3 times 4 is 12. The x, that base, always stays the same. And then our new exponent is just one number lower. We literally subtract 1. And then minus, because it's a different, we need to take the derivative of 7x. That's a linear function, so the derivative is just the slope, or the coefficient. And my friends, it is that simple. That's all you have to do. If you then want to multiply out the 1/6, you certainly can, but unless we're in a multiple choice setting, you don't even have to do that. You can just move on with your life and finish there. Letters B and C are different, and because they don't look like power functions, at least immediately. And perhaps you can see how we could make them look like a power function. And if you want to pause your video, you could go ahead and try those too. I'll certainly give you that time, and you can give yourself that time just by clicking pause. But otherwise, I'll start up in just a second here. Okay, whether or not you paused the video, the key here in letter B and letter C is to rewrite the function as a power function. And so 1 over x to the third, maybe you notice that this is x to the negative third. And we should change this really to g of x, my apologies. And so from there, even though it's a negative exponent, it's still a power function. So g prime of x equals, we're going to take the exponent down in front. There's no coefficient, so the exponent becomes our new coefficient, x. And then we're going to do -3 minus 1, which is -4. And to be perfectly honest, you could leave the answer just like that, but often we see these problems in a multiple choice setting, and that will more than likely not be the answer you see on multiple choice. It will be written again back to positive exponents. So it would probably be written like this, -3 over x to the 4th. And that is exactly what you would be looking for. That is a beautiful answer. And if you got that all on your own, congratulations. Letter C is very similar, except we're not dealing with a rational function. We're dealing with a radical one. So again, it's important to rewrite this function as a power function. And we should know from Algebra 2 and pre-calc that the cubed root of x is the same as x to the 1/3 power. And then from there, even though that's a fractional exponent, it is very easy to take our derivative. So that means we're going to take the 1/3 down in front. There's no other coefficient, so that becomes our new coefficient. And then we need to do 1/3 minus 1. With fractions, it might help you to visualize a common denominator. 1/3 minus 3/3, or minus 1, is to the negative x to the -2/3. And again, in a perfect world, we'd be done, but we usually see these in multiple choice settings, so I'm just going to rewrite that with positive exponents and without a fractional exponent. So that would be, all of this is just 1 over the 3 here becomes just a 3 in the coefficient of the denominator. And then x to the -2/3, the negative has pushed that x to the denominator, and then x to the 2/3 means the third or cubed root of x squared. And that is exactly what we're looking for here. All right. If that moved a little quickly for you, feel free to replay this part of the video. We're going to look at number 5, or at least part of number 5, letter A specifically. And this is not too bad. Let's read the question. It says, find the slope of the graph of f of x equals x to the 6th when, and then it gives you 3 different problems. First and foremost, in order to find the slope of the graph, that's just a phrase meaning find the derivative. So we're going to do that. The derivative of f of x can be written and should be written as f prime of x, and then we just apply the power rule. X to the sixth, if we're taking the derivative, 6 comes out in front, x to the 6 minus 1, which is 5. So for all three of these problems, all I'm doing is plugging in the x value into that equation. So if I want the slope of the graph of f of x equals x to the sixth when x equals -2, that's another long drawn out way to ask for f prime of 2, which means f prime means I'm going to use 6x to the fifth, and -2 means I'm going to plug -2 in for x. So 6, -2 to the fifth. And from here, ideally, it's mental math and arithmetic, but if you need a calculator, we're early enough on in the year where you can do that. So this becomes 6. I happen to know that -2 to the fifth is -32, and I also happen to know that 6 times -32 is -192. And usually, almost always, unless there's something really tricky going on, when we find the derivative at a point, we should be getting a numerical answer. To that end, I'm going to ask you to do letter B and C on your own. Letter A gives enough of an example where B and C can be handled individually. If you're struggling there, you can either wait for the answer key, or you could put a question in the comments, or you could reach out to your teacher. If I'm not your teacher, you could also reach out to me, and that's no issue whatsoever. We're only going to do one more problem together, and that comes out of number 6. A and B and C and E are problems you should be able to handle. And again, if you need help, don't hesitate to ask. But letter D is just a little too gross for me to leave you on your own right now. And the way we handle letter D is very similar to how we handled the first couple problems we worked together, is by rewriting that function with maybe negative exponents or fractional exponents or both, so that we have a power function. So why don't you take just 30 seconds or so, see if you can transform f of x in letter D into a power function, because right now it is definitely not one. Go ahead and pause the video and try that one. Even if you're totally way off, it's still good to try it without me walking through every single step. So go ahead, pause the video. Cool, welcome back. What we are going to do is we are going to rewrite f of x. So this 1/4 becomes a coefficient, and we have the cubed root of x squared in the denominator, which means that whole piece, this whole thing, can be written as x to the -2/3. Sweet. Give yourself a little pat on the back if you got that on your own. And then if you can take it even farther, that's incredible, that we're going to take the derivative now, because that is, albeit a very gross power function, it is a power function. So the way we take the derivative is by multiplying the exponent and the coefficient together. If we multiply those two fractions, we get -2/12, or we get -1/6 when we reduce. And then we're subtracting 1 from the exponent, and I'm again going to write that instead of 1 as 3/3, because this is most definitely a non-calculator problem in the AP testing world. So I would get -5/3. And gosh, don't forget your x there. That's the most important piece. Okay, again, when we write this final answer, we can do -1/6 times the cubed root of x to the fifth. And actually, because there's an x to the fifth under a cubed root, we can be even cleaner and write -1/6x, because 3 x's come out of that cubed root and make 1/2 x's, or an x squared, left over. So Either one of those is going to be acceptable. The one on the far right is probably going to be the choice on the AP test. But again, you don't have to be perfect just yet. Our goal here early on in this unit is to make sure you're just understanding how these rules work, so you're not creating a limit expression every time you want to take a derivative. That would be crazy, or at least really time consuming and a tad boring. Okay. I'm going to put all the answers, 1 through 6, including the warm-up, in the answer key that will eventually be posted alongside this video. If you have questions in the meantime, don't hesitate to put the questions in the comments, talk to your teacher, and if I'm not your teacher, let me know. Thank you for your time. Thank you for being here on YouTube with me. And again, it was great working with you. If you have any questions, please be sure to let us know. And we'll see you next time for 3.4. Thanks, everybody. Have a wonderful morning, afternoon, evening, or night. Get some sleep. Bye.